right. Yeah, welcome to the last session of the day. I'm really grateful that you're here. Edge native. So next half an hour, we want to go and chat a little bit about how to bring the cloud experience to the edge. That's what we call edge native. So back in 2010, roundabout, everything was on-prem. And then everybody started to swiftly move their workloads to the cloud. And we've seen that height, maybe 2015, maybe 2018. But since then, we see the pendulum coming back. And there's a couple of reasons why the pendulum kind of swings back, as we all are aware. Like, one is privacy regulations, and regulations are increasing, so certain things have to run on-prem. There's real-time performance, and we heard it all across today, and probably many times every day. But there's also cost, right? Because lots of people discovered that the cloud is not for free. And, well, maybe because of that, we want to go and run stuff on-prem. But as the pendulum swings back, I think there is one thing that we don't want to lose if we go back to the edge or to on-prem. We don't want to lose what we love about the cloud. So the real question is, can we make the edge feel like the cloud, especially from a development perspective and from a usability perspective? So what is great about the cloud? It's easy. So let's go and see whether we can hide away some of the complexities that we find while going to the edge. Resource constrained, remote, hard to reach. From a cloud perspective, we also deploy really, really quickly. So we don't want to go and roll hardware every time we deploy something. So we want to go and preserve the speed. And even more importantly, we don't want to learn a new tool chain. I can hire loads of people that are very, very familiar with cloud tool chains. It's very difficult to go and hire somebody that knows a specific tool chain for a specific solution that was built for edge. Yes, I can maybe hire one and train that one, and then the guy might be gone, and then I have to go and start over. So the real question is, can we preserve what we're all familiar with? Which means, like, can I preserve my Docker toolchain as it is today, my Kubernetes toolchain as it is today? So if I have somebody that is trained to go and Helmify applications, maybe I need to go and add a little bit of pixie dust on top of the Helmification, but not more, please. Don't have him start over and learn a new packaging tool. So I talked edge. There's many edges, as we all know. The Linux Foundation gave us a great nomenclature for which edges, starting all the way from very constrained devices, so the sensors, all the way to centralized data center and cloud. And if you approach edge, you can go and approach it from the right-hand side, which is what Gartner calls cloud out, which means you're extending the cloud operating model towards the edge. And that means pretty much like you're trying to go and treat every single region, every single edge like a region. Or you start to approach it completely the other way around. You're starting from an assumption that everything is local, everything is autonomous, and maybe this everything might reach out to the cloud every now and then to understand what it needs to go and do. But otherwise, it's autonomous, it's in its decision making. When it's going to go realize something, it's going to go do that at its leisure. And it's going to coordinate locally. And even more so, if you're doing this locally there, you have to go and deal with entities that are operated by non-IT staff. Don't assume that in a McDonald's, Starbucks, or whatever, you find somebody that is really IT savvy to go and debug and fix it and whatever. No, the maximum that they can go ask the guy to do is power cycle or hit the factory reset switch. That's it. Where I'm going to go and focus is where the cloud model breaks down, this extend the cloud, and where we really need to go edge in. Because this is where the transition really happens. This is where we have to rethink the operational model. This is where edge native starts, because cloud native doesn't do it anymore for me. And what are these smart device edges? I think the crystal point where this whole thing kind of transitions. You've all seen that, right? You've seen that if you ask for what type of compute is running in my local coffee shop, what type of compute is running in my local burger restaurant, what type of compute is running in the bus or truck that monitors the roadside. So you've seen all these use cases. This is where kind of extending the cloud model all that way won't cut it. We have to go and do something different. And what we see at the smart device edge, because we've seen people deploy solutions at these spaces for quite a while, but right now we're seeing a real transitioning happening. Historically, I think that was the first and the second phase of IoT-style deployments or edge-style deployments. We've seen people put monolithic solutions for a single purpose in, so single trick ponies for a particular problem. Smart mirror, here's my solution, here's my entire solution stack. And these things are transitioning because people are piling up more and more use cases into a particular location. If you've seen the transformation for retail stores, for instance, from going from a shop to an experience center. So we want to go from vertical point solutions to a platform approach. Along with that, you are not going to go and deploy a new piece of hardware every time you come up with a new solution. Moving forward, you're going to go choose one type of compute equipment, and if you put the next use case, you're just horizontally scaling that in a per location basis. So you're not going to go and choose hardware anymore on a particular purpose, which is really a transition, because in many cases, even if you run AI today at the edge, you're looking into like, how many FPS does this particular platform do with this particular model? Moving forward, if you go into a clustered approach, that will not be feasible anymore. And obviously, yes, we don't want to go and roll a man in the van every time we have a new application rolling out. So we need to go from something manual to something completely automated at these edges. So what does this deployment scenario look like? You have a little cluster that runs at the edge out of these kind of general purpose compute units. And then, yes, you have inputs from sensors and cameras that serve as a sensor because they're on an AI model. And you have outputs to local screens, like for digital signage or control screens and whatever. So there's always typically one element that also has output to it. And then you have a long WAN delay, whatever WAN link. So that constraint is pretty important because that hinders the cloud to be all the way extended to that very smart device edge. And the biggest factor of this whole thing is we're not going to go do this once, because we probably do this n times, 1,000 times, 100,000 times, 1,000,000 times. This is where some of the complications come in, so that you can go and not deploy it once or twice. I can always do that. I can babysit that. But as soon as I scale out, I have a completely new question that I need to go and answer. So if we're going from cloud native to edge native, what does that really mean? It really means that we have to go and rethink certain principles. And what are kind of the main cloud native principles? Because we called them main principles even before cloud native, the term was really invented. And that goes all the way to the guys who gave us the 12-factor designs. And that's the Heroku guys back in 2011. And if you look at the 12 factors that Heroku and the team in Heroku gave us back in 2011, they're very stable. So they came up with something that is stable for more than 10 years from an application design principle perspective if you're building something that is really cloud native. So separation of code and data, clear definition of dependencies. So all of these things, I think, are mostly valid. But if we put the edge color onto it, we have to go and rethink these slightly. And rethinking them slightly in many cases means putting the notion of location into the mix. So as soon as we're declaring dependencies, these dependencies are no longer only dependencies from a software perspective, but they're also dependencies that translate all the way from where these things are. If you have backing services, it's that these services can be remote, and how do you reach out to those? If you look at concurrency and scale, you're not only scaling by process, you're certainly scaling also by location. Same goes from a redundancy and disposability perspective, and logging we'll touch on in a little bit of time. One key principle that we have to adhere to is in the cloud, we scale by the number of running processes, the number of workers. We will continue to do that, but only on a per location basis. But now you have these many edges that times n. That means I have a new dimension that I need to go and add to my consideration list. So I'm scaling by location. And what does scaling by location mean? I'm scaling by the number of sites, and sites are physical or logical grouping of things, of compute nodes. And I'm applying applications or deploying applications to particular sites, not to individual nodes, because we want to go and treat a cluster as if it would be one unit, multiple units. So these little sites are kind of bunches of little compute nodes. Could be one cluster, could be multiple clusters. Let's abstract the notion of a cluster, because that's something that Kubernetes wants. It's not something that a deployer would actually think about if you're looking at this as an abstract notion. And these sites are disposable. So these sites are cattle, because I can't really treat 100,000 sites one by one as if they would be pets. So these things are like, they can be stopped at any point in time. They can trip over, they can fail at any point in time. So my failure model is not that, oh, there's something going wrong in, well, whatever this little cluster in San Francisco might be. I'm not going to go and SSH or terminal connect or what. I'm never, ever going to go do that. If you ever saw like how people say, recently I saw somebody debugging a point of sale terminal, the store manager in McDonald's. What did he do when the box blue screened? He opened the thing, he flipped the switch, and hopefully it boots. If it doesn't boot, big red banner. Done. Replace. But you're not going to go debug that. So don't come up with an operational model that even requires me to ever SSH to that box. It's not meaningful. Let's build something that we can completely run in a completely decorative way. Backing services, yes, the old declaration model still holds, but these backing services might be remote. And these backing services might be remote in a way that I can reach them, but they might not be able to reach me. So I can go and reach the cloud, and I think that probably works for most of these remote locations, even if there is a long delay WAN link in there, something DSL, whatever, multiple nets. I can probably reach the cloud, even if it goes via multiple intransparent proxies. But that the cloud can reach the edge, so that the cloud can really extend to the edge, don't believe in that. And also don't expect that tunnels will work. I grew up in Cisco for quite a while, and the one thing that everybody hates in the company, despite the fact that we've built 1 million tunneling technologies, is tunnels. If you want to find anybody that really loves the VPN on their laptop, anybody loving their VPN on the laptop? Is everybody trying to avoid using the VPN at all cost? I only turn it on if I really have to go to certain sites within Cisco that Cisco believes have to be on-prem. But in most of the cases, like, yeah, well, I don't really have this VPN on, because it creates all kinds of headaches. So let's go and assume that the best thing that we can go and do is reach out to the cloud, fetch state, and pull it back in at my speed, at my leisure. And I can go and push state to the cloud, metrics. That's OK, because I can go and reach the cloud. If I want to go and push stuff to the cloud, yeah, historically, it was all about like getting logs off the box. That's what the 12-factor the 12-factor design told us. These days, we all know logs are great, metrics are better, because metrics are more compact and contain more information, because that's already pre-processed information that you can push out. So use metrics wherever you can. Use logs only if you have to, because if you turn on all logging, it might be the last thing that you heard from that particular site, because then you clog the WAN link to go do nothing else but trying to go and push your logs out. The other thing is, even if you do metrics, we found that there is too many metrics at a particular edge location that we can go and get. So we need to go and filter at the edge. So we need to go and focus on information rather than sending data. And we've spent a fair amount of effort in that. Actually, 2 of my PhD students focused on this whole problem of how can I go and do, in an unsupervised way, do filtering of metrics at the edge, so that if you see certain things happening, I'm only sending those metrics that are likely describing what that particular event is, instead of a bunch of rubbish, right? So don't send me 10,000 counters that all changed because an interface went down. Show me the 3 counters that really describe why the interface went down. So there's quite a bit of effort in that particular area. So if we apply this edge native principles, what does that mean if I'm designing a platform and we are running an experimental system that we are kind of in the process of getting into the community and into open source? So let's again take a step back and look at Kubernetes in an oversimplified way. What is Kubernetes in an oversimplified way? I have my customer, and my customer tells the system what to do via an API server that puts declared state, what I want the system to do in a database. And then my individual workers are reaching out to that database, what the declared state should go and be, and realizing that state. Fine. That makes my overall system a pet, and the individual workers are obviously cattle. Now, if I'm going edge native, I need to go and scale by location. So I can have a cluster or multiple clusters per location, and I can go and treat these little individual things as cattle by applying the same principle with a clusters of clusters methodology, where I have a global API that says, OK, this is the declared state what I want for my system or subsets of my system. I put that into a DB, and then I need to be able to go and have these individual sites reach out and grab the declared state at their leisure and implement the declared state. And for that, I need some intelligence, and we call this edge operator, this little piece of intelligence that I need to go and run at the edge that allows me to frequently reach out to the cloud, get the declared state, and then realize it locally. That also allows me to go and horizontally scale forever from a locations perspective. So within the location, I can have classic Kubernetes scaling by process. Across the locations, I can apply the same model and the same logic. And yes, I'll run my typical other infrastructure, like I will run a Grafana agent so a lightweight version of Prometheus to go and collect metrics. I'll run a Prometheus exporter to go and get the stuff up. So the remainder of the official cloud-native toolchain I will continue to use. I'm not going to go and reinvent the wheel, because from an observability perspective, I want to use my existing toolchains like Thanos and all the other good stuff. So let me go and give you a little bit of eye candy of what we're working on. That's kind of a preview. You can help us join the party and help us develop this thing. And as I said, we're on a route to go and make that available at a broader scale. So like kind of where Nephew is today. So what I want to go and do is roll out an application, roll out a new site and deploy that app. And just to remember, apps are deployed to sites, and sites are collections of small computers. So small computer could be a Raspberry Pi. That's the smallest entity. You could go and run stuff on VMs. You can run stuff on, say, NVIDIA Jetson or other devices. What I'm assuming here is I have bootstrapped the whole thing. It's up and running. It has a serial number, and that serial number I'll later on use in order to claim the device into my system. So we're going to go and define a site, boot that up, add a node to the site, that's a little compute element, and then deploy an app. So if I enter the system, yeah, I have a list of sites already up and running. You can go into a map view, and actually that map view shows all the location of people in the team that we have working. And so most of the team is in Europe right now. Where I don't have anybody up is where I live in Germany. And I'll actually live in Cologne, Germany. And let me go and create a site called Cologne. So that's my home office. And now if you want to go and send me nice email and postcards from all over the world, I live in Gutenbergstraße 26 in 5826 Germany. But only nice mail, please, right? So we have my little site. So you see that the site is up. Next thing is we need to go and add a node. Now we need to go and remember the hardware ID to go and claim the node, bring that up here, and we're going to go and give the baby a name, like the Cologne node. And, well, it's my Raspberry Pi that I used up here. And if I enter the details and click Apply, then you'll see this thing going from no status into bootstrapping. What happens at that particular point in time? We install a full-blown runtime on this based on lightweight Kubernetes. So we're not reinventing anything here. We're just assembling stuff that is there. Once we have the node up and running, I can go ahead and deploy an application. So I'm going to an application store. There's not too much populated here, like typical stuff that you find at the edge, like MQTT brokers. Here I'm going to run a simple hello application. It's a HTTP echo application based on Python Flask. It's a couple of liners. I'm saying hello from Great Bear, and I'm going to go and put the port that I want to go and reach it at. Then I'm putting deploy. And what happens when I've put deploy, I put the declared state into the cloud, and then the node will fetch the declared state and realize it locally. And that takes a while. So it depends on how fast this node is until it is installed, it's in the process, and then at some point you can go and run it. And well, just for matters of completeness, we're going to go and run that real quick. The running thing is the most boring part ever, because you're going to go and HTTP to a node, and then the node will tell the story that we told it prior, like hello from Great Bear to the one summit. So that's not overly interesting. But it shows the concept to go and make these individual nodes autonomous in their behavior and only fetch declared state at their leisure and realize it locally. You can apply the same principles if you do application development. Apparently, you have to, because there is no imperative control to applications if you're running them at the far edge. So what we found from the most common needs is, yeah, well, you need to have something data management. So that's the classic IoT world. Ingest data, transform data, and push it out. Edge AI, I'm going to go and focus on in a little bit of what we have to go and do that space. I want to go and show you a little bit of eye candy also for the rendering piece, because I said, like in many cases, these nodes have locally attached displays, because you want to go and show something, whether be it an RTSP stream from a camera or be it like the results or well, something like digital signage, render content that was declared in the web somewhere else. And from a kind of access pattern perspective, it's very edge native again. Like you're specifying in some dashboard what content to which locations, and then these locations will fetch that state. Like I say, well, go and display Cisco.com. They'll fetch the request, and then they are reaching out locally, pulling it, and then rendering it locally. So showing you the system, we have this event-driven display deployed on 3 nodes here. And then on the right-hand side, you will see VNC connections, so kind of showing the local screens of this particular thing. And well, I'm going to go and do poor man's digital signage for you. So the first thing that we're going to go and render is Cisco.com to all these locations in one bulk update. So I'm going to go put the declared state in as render Cisco.com. And then you'll see that these guys, once it's arrived, they'll start to render. But not everybody at the same time and not everybody at the same speed, because it depends on how you realize that intent locally. And then you can play around with that. Like you can go and say somebody like, oh, please do and render an RTSP stream. And what is a public RTSP stream? It's Big Bug Bunny. So we told Rolle in Switzerland to go and render Big Bug Bunny. But I can also go and consider hooking things up to public digital signage providers like ScreenCloud, for instance. And one example that we have here in addition to that is like hook up one of the sites, apparently the London site, to ScreenCloud, where I just say, OK, load that particular URL for ScreenCloud, and then it gives me a pairing code. And I can go and switch to ScreenCloud and pair the screen, and then I can go and remote that and control that screen remotely. That will only work if that particular digital signage provider will also adhere to edge native principles, right? So that this control screen here fetches state from the cloud instead of you imperatively push that state depending on your deployment scenario. Well, you can go and obviously play with this and say render the local weather. Fine. One step further. So this is local rendering. Where it gets really interesting is if you're looking into Edge AI. And there we have a little bit of a challenge based on this means that we're no longer choosing hardware based on the requirements of a particular model, but we want to go generic. So I want to go and deploy an AI model to these sites, and these sites are clusters of general compute. So I'm no longer saying, well, AI model, you have to go and run on Xavier NX from NVIDIA. But yeah, well, you're running on a bunch of devices that have certain capabilities, and they might not really fit your model. So it might well be that you have developed 2 AI models, and the first one requires 100 meg, but I don't really have room for another 100 meg on my edge device. What do? Bummer. The second one I developed, it runs, but it's freaking slow. So it might run at 2 frames a second on your target hardware on a single node, but you need 5. Why is that, right? So if you do, say, people counting at a front door, if you run at 2 frames a second, you might not notice that there is a little bit of a person overlap here. If you're running at 6 frames a second, you might see that, well, these 2 people kind of delineate every now and then, so I detect 6 people. So running with accuracy is important. So what can we do about that situation? The first classic thing was always like, I select the hardware, and then I put my model onto the hardware, and everything is hunky-dory. Yeah, but that means I kind of select the hardware, and I roll it on an individual basis, which is not great. So I can throw hardware at the problem, check. The other thing is that everybody does is you compress the model. So you're going from floating point operations to int4 or int8 for inference. You're optimizing the model and seeing, well, what is my labeled data? Do I'm using all the paths through the model, or I can go and compress the model? I'll do that. But what if it still doesn't fit? And we've started to explore, like, if it still doesn't fit, can't we do what we've been doing in networking forever, i.e. distribute the problem? So can't we just like take a model and then just say, well, the first 10 layers on this node, the second 10 layers on this node, and the final 10 layers on this node? Very straightforward in hyphens. Because this splitting at a broader scale, not 1, 2, 3, but if you make it a little bigger, is an NP-hard problem. But the base idea is really to go and take the first portion, run it on one node, and the second portion I'll run on another node. Another thing to go and consider is it's not only the performance of these individual nodes that you need to take into account, it's also the bandwidth in between. If your bandwidth is, and that's from experience, if your bandwidth is less than 1 gig, then you're going to have a hard time. Because most of these models communicate quite a bit between the individual layers. So you not only have to go and choose a layer-to-layer split where maybe there is not so much communication going on, but you also have to go and adhere what the compute capabilities are. So like, there's a lot of balancing out, finding an optimal split. And we typically run a profiling phase before we do the split of a particular network. What can you do with that? If you look at, like, on the left-hand side, we are running a model on an Onyx runtime, single node, 1.1 frames a second. Doing the same thing on 2 Onyx nodes, same runtime, I can go up to 1.7. Why don't I double? Well, I'm keeping the nodes busy with communication backwards and forwards. So the nodes need quite a bit of quite a bit of compute in order to push data backwards and forwards in that particular case. I can go higher if I have one of the nodes optimized for another runtime. So if this node is optimized to run T of light, like in this particular case, I can obviously go higher. But what that shows is I can indeed split and conquer. So what that means in a nutshell is that the old trade-off where I'm saying, well, if I need to go faster on a particular piece of hardware, I need to choose a model that comes with lower accuracy. So that's the old trade-off, right? So you're not fast enough, go and take a simpler model. What I can do now is I can go higher FPS, stay with the accuracy by throwing additional hardware at the problem in an incremental way as pay as you grow. So that's quite interesting. Final thing, model training also fits the model or the edge native principles really well. So if I need to go and train an AI model but can't really get access to the customer's data, so I want to go and train in the cloud but I don't have access to the data, what do? You do federated learning. So you learn at the edge. What does that mean? You have a global model. You distribute the model to the local edges. These models are trained with the private data that you have. And then you only upstream the weights, the learned weights of the model adaptation that you've done at site 1, 2, and 3. So you push data and you pull data, and it's very nicely matching to what you can go and do from an edge native perspective. Which is why, yeah, well, there is a piece of open source that we've built for that particular case. It's a framework called Flame to go and help you distribute federated workloads that you can go and then, well, run at multiple edges. In summary, and that goes all the way back to the keynote that we've seen from our friends from Amazon and Dell earlier on today, is by moving from cloud-like to edge native, we also enable an industry transition. And that transition that I was hinting at earlier on. So we had in the past that the second phase of IoT, so to say, we have all these single trick ponies. You have a smart mirror, solution 1. You need people counting at the door, solution 2. You want behavioral analytics for your people in a retail store, solution 3. All of these guys come with a siloed solution, hardware, software, control system, management system, all nicely siloed. And guess what? People don't like that. If we really go edge native, we can platformize. And that's awesome. So we can go and choose the hardware independent of the apps, and we can even build the apps independent of the underlying hardware. And I think that's the journey that we're on. If you want to learn a little bit more about that or even join the party, as I said, like we're working towards getting this overall experimental system into people's hands. We're working with a handful of people. We're happy to go and have more people join. Go to greatbear.app and sign up, or have a look at what we have. There's a couple of documentations out there. I wrote a blog a while back, and I also published a couple of demo videos, more detailed than what we have here on a YouTube channel. And with that, thank you. And if you are not desperate to go for a beer, I'm happy to take any questions, if there are any. There are one. Yeah.
Earlier you mentioned there are two approaches. Hyperscalers choose this cloud-out approach, and there's edge-in approach where things are more autonomous. Do you endorse one over the other? Do you think one is the right approach? Or
no, that's a good question. So I think the basic question is there a right or wrong between edge-in and cloud-out? Obviously not, right? So the problem is that cloud-out doesn't really go to the very far edge. And then you have to rethink what you're doing. If you have an environment where that's not a problem, you can go and run everything in an imperative way. If you are really far out, and if you have this scaling problem across a number of locations, and not only from a process perspective, then you have to rethink what you're doing, because then it might be that you're starting really edge in. That's your starting point. That's your focal point. And then you're really welcome from an edge in perspective to treat the cloud as yet another edge. It's a really big edge, but that's fairly okay, right? That's not the problem. So edge in is probably more inclusive than cloud out, but in many cases, cloud out will just work. Good question. These guys are desperate for a beer. So enjoy the booth crawl, and well, I'll be around. Thank you so much. Have a good day.